Deep. Did I say that right? Where's Madeline? Oh, she's remote. Okay, she's a remote presenter. She is online. Okay. So this is going to be our first attempt to do a remote presenter, so bear with us. Madeline, can you hear us okay? Is she unmuted?
She can do it in the text chat.
Is she texting or anything over there in the chat window?
Can you hear us now?
Yes.
Yes, hello. Well, my name is Gudjon Magnusson, and I'm a research scientist here at Fraunhofer Center for Experimental Software Engineering, and I'm going to be the presenter today. So good morning, and sorry we couldn't be there in person. Hopefully this will work. So we're going to be presenting some work that we did as part of the NASA Software Assurance Research Program earlier this year on modeling requirements for autonomous systems. You're controlling the slides for me, right? Someone? Thank you. So the motivation for this project was that there's a strong interest at NASA and pretty much in every domain to move from just automation to more and more advanced autonomous capabilities. But the challenge is that assuring autonomous features is still an open challenge. So this project is really focused on how can we get to better specifications of autonomous systems and lead to better assurance for those systems. So next slide. So just a quick outline. We're going to give a brief sort of definition of how we're treating autonomy and what requirements for autonomy look like, and then show some models that we put together, graphical models, and give a quick overview of sort of the analysis that you can do with those models, the sort of key indicators to look for. So you can move to the next slide. So with autonomy, there's all sorts of different definitions for autonomy. It's commonly said levels of autonomy for autonomous cars or for drones or whatever domain you're in. We're not very picky. We're essentially just saying an autonomous feature is just a function that needs to be completed without human intervention. An autonomous system is simply a system that has at least an autonomous feature. But it gets a little trickier than that, I suppose. The next slide. It's very easy to specify autonomous features at a high level, such as go from A to B and don't run into obstacles. And these are the sort of high level autonomous requirements you might see early in a project. But when you really start to break down what that looks like in detail, it gets almost impossible to specify all the different things that could go wrong, all the different conditions that may ruin that functionality. So the requirements have to be extremely detailed and specific, and it's essentially impossible to cover the full space of options. So we go to the next slide. So for our definition here, autonomous requirements already describe some behavior that needs to take place in a dynamic environment based on the available information. So there is some uncertainty in the environment that you simply cannot engineer away. So if you ask me, I would say the autonomy has much more to do with the environment that you operate in than necessarily the feature itself. Because in a controlled environment, you can do pretty much anything. But if you send something to space and you have to count on it, doing its thing, and you don't know what's going to happen, that's where the autonomy gets complicated. And since the functionality or the behavior cannot be fully predetermined, it's extremely complicated to reason about the completeness and correctness of the features ahead of time. So we go to the next slide. So our approach was really to model autonomous requirements. So why do we want to do models or graphical models? So Fraunhofer has a long history of doing model-based testing, model-based engineering, and it's really been shown, I think, that once you start to model something, you really gain a better understanding of what's going on. Even if the model itself is not useful, just the act of modeling teaches you something that you may not have seen before. So it gives you a level of abstraction that sort of removes the details that don't matter, and it lets you see sort of relationships that you may not have been obvious at first. So if you take natural language requirements and you start to really think about how, the model, exactly how the behavior works, you may see gaps in requirements or conflicting requirements that were not obvious before. And this is common practice with requirement engineering. But what we're really trying to do is see how can we apply this, get these same benefits, but for autonomous requirements. So if you go to the next slide. Yeah, so that's what I just said. So if you can model the autonomous requirements such that engineers can gain additional insights into the nature of the uncertainty they're dealing with and what really is the behavior they want the system to achieve in that uncertain environment. And if you can do this early, from early requirements, you can reduce the risk of errors and miscommunication as the project moves from design to implementation. And if you have good specifications, you can do good testing, which is of course a challenge. If you're trying to test a system and you don't really know what it's supposed to do, then what are you really testing for? So we can move to the next slide. So the focus of this work has really been to understand what are the useful abstractions that we can apply to autonomous functionality. So if there's different from regular requirements, let's say. And if you go through the motions of modeling this behavior, what type of indicators can you look for? What type of lessons can you learn from these models? So let's go to the next slide. So we took a broad approach looking at what modeling methods existed out there for requirement engineering and what existed sort of specific to autonomy or cyber-physical systems or AI systems. And we found these 4 methods are particularly interesting to us. Or we found a few methods and we adjusted them to our needs. Since we couldn't really find the silver bullet of like, the challenge was to figure out what is the right time in the life cycle to do this and what is the right level of abstraction. So the process is really, we ended up really with a process going from the very vague, very early, high level to the very specific and very detailed. And we found different methods to guide us through the process. So it starts with generic autonomous requirements, which is work presented by Michael Hinchey. And that is really the only thing that specifically mentions autonomy in it. The next thing is the goal-to-competition models, which is we just took from goal-oriented requirements engineering. And then we go into agent-oriented modeling, which there's quite a bit of literature on, but we adjusted a little bit for our needs. So we're going to go a little bit into these different modeling approaches in a bit more detail. So if you could just jump to the next slide. So this is our little case study. One of the challenges always, if you want to work with, we did this work with NASA, but they were reluctant to give us their systems, understandably. So we sort of came up with our surrogate system, which this started as a small project just between me and some interns here at Fraunhofer. It was just a small rover that drives around the halls. And we came up with some requirements and tried to model them using our approach. So the domain is, it's a small rover that drives between offices and delivers small packages. So if I want to send a note to Madeline through the physical world, I can put it on the rover and it would drive to her. So we'll just go to the next slide. So the generic autonomous requirements, as I mentioned, proposed by Emil Vase and Mike Hinchey. It really starts at a very high level, sort of gives you a way to categorize, I would say, autonomous behavior, giving it, it uses the common self-star requirement format. So you could say the autonomous system should self-navigate, self-plan, self-heal, and however you would want to define that. And the video just cut out. Sorry, can you still hear me?
Did we get cut off? We all right?
Okay, I can't see, but you can still hear it, maybe.
Yes.
Okay.
Yes, we're hearing you.
Okay, I'll try to go on without the video. So each of the high-level self-star requirements is supported by sort of the sort of more detailed requirement, such as awareness. What type of environmental things does the system need to be aware of? Or robustness. What type of errors or sort of problems do you expect the system to have to deal with? And this method really gives you sort of almost a checklist approach, because an autonomous systems that let's say versus a underwater vehicle, they're going to have very different problems to deal with, and these sort of checklist approach allows you to sort of bucket the features into similar functionality. And the idea being that once you figure this out for one system, you can sort of transfer the lessons onto another one. So this is work that we sort of chose as being sort of an entry point into our 3-level modeling method. So we go to the next slide. So the first model that we sort of defined is the goal decomposition model, and it's really adopted from goal-oriented requirements engineering, or specifically the chaos method, which is a great deal of literature on. What this does is it lets you sort of model the relationship between high-level goals and the requirements. The goal really is to understand not only what the system should be doing, but also why. So gain traceability from the detailed requirements up to the high-level system goals. So this graphical model looks essentially like a tree graph, where the root of the tree is a high-level system goal, and each level below that is a supporting sub-goal. And the tree is complete when every goal is supported by a leaf node that is a goal that is specific enough to be implemented. Or in this work, we really, once it is detailed enough that you can assign it to an agent, is how we define it, is when it can be considered complete. And that feeds us into the next model, which is the agent interaction model. If you go to that slide. So the term agent it can be a loaded term. So people have different associations. I think it's worth mentioning that we're not considering this as some sort of a implementation thing. There are various frameworks and languages and whatnot out there for implementing agents, but we're thinking of this as a abstraction that lets you sort of organize autonomous functionality and autonomous features within a system. So the requirements that you discover in the goal model are assigned to agents, and the agent interaction model is meant to highlight how the different agents of the system interact. And it shows the actions that have been assigned to each agent and what information these agents share in order to perform those actions. So we mentioned information quite often because the way we see this, autonomous systems are very information-driven. That is to say, they're reading sensors, they get commands from mission control or whoever, and the really important part is how do they respond to this incoming information.
So Gurdjieff, we have a question for you.
Yes.
Hi. Hello. Hi. Could you clarify, please, what you mean by agent? Are you talking about a separate cyber-physical system, or you're talking about a different function of autonomy within the same system, or maybe both?
Yes, exactly. So, I mean, again, because people have different associations with what agent means. So we're really considering agent to be essentially some component that can take care of the work. There may be, for one, let's say a robotic system, we consider there could be multiple software agents, but there is also the room for possibly being external agents. So an agent could be a human that needs to do something that has a role to play within the system, or it could be, a separate entity, another robot, another computer, a server somewhere. So it's just meant to be an abstraction for some role that needs to be played within the system. So let's say some non-trivial autonomous functionality tend to be done.
All right, thank you for the clarification.
Okay, so within this system, this is a little case study. We considered a few agents that were within a rover, plus the humans that interact with it. So those were the agents. Anyway, so what I was talking about is we tried to sort of categorize what types of information the system may need to respond to. And we came up with these 3 categories, which is messages, which is essentially sort of explicit event-driven information passed between agents. Another category is knowledge, or sometimes say knowledge base, which is really persistent information stored in memory and used at runtime. And this, you can imagine really 2 types of persistent information. You can imagine a rover who's driving around, mapping out its environment through sensors and remembering where the obstacles are. So that would be information that is changing at runtime. The other option is sort of static information that's given, at design time before running the system, such as, just the laws of physics or the position of certain things and in the world. I don't know, the diameter of the Earth. And the third type of information are percepts, which is really real-time information from the environment. It's really the sort of the most up-to-date notion of what the world looks like. So this could be raw data, such as just reading a temperature sensor, and that's just one value which reflects, the state of the world. Or it could be something more complicated, like you take a picture through a camera, you run some processing on it, and you figure out, where the human faces are or where the obstacles are. But that's still one percept. And so, just to summarize, the goal here is to show what are the types of information that the agents are relying on to perform their actions, and how do these agents interact? At what point does one agent, let's say, interfere or assist another agent in performing the bigger system level goal? So you can move to the next slide. So the next model, and the fourth and final model that we have, is the most detailed one, which is the agent decision model. So here we really wanted to sort of elaborate on precisely what actions does the agent perform and when does it do it in response to the available information. So, and by actions here, we're not thinking of sort of trivial like software things, but it really intended to be sort of long-running computational tasks or physical actions like moving a robotic arm or orienting the satellite. Some important actions that have consequences, let's say. And initially, we thought of this sort of as a state machine, but we end up renaming it to sort of embrace the idea that actions take time and the world is not closed. Information can come in at inconvenient times when you're not really wanting to get it. So the idea is to show when the system is doing something, how is it going to respond to incoming information? Okay, so now I'm gonna try to go and move quickly and go into how we applied these to our case study. So if you go to the next slide.
Good, Jeff, you there? Good, Jeff. Okay, so we lost you and can't hear you. I don't know if you can hear us, but yeah. Okay, so we'll try the chat, maybe. Any messages? Okay, good, Jeff. Can you hear us? Can anybody in the chat can hear us? Okay. Okay. I can hear you.
Okay, so I think his connection dropped.
Yeah. Okay. All right.
Do we have a way that maybe we can email him or something?
Yeah, I can send him.
Hello, sorry, can you hear us? Am I back in the room?
Okay. Yeah, we can hear you.
Sorry, I disconnected there for a while. I'm not sure what happened. And I just realized that I'm maybe a little short on time, so I'll spare you the nitty-gritty details of everything. So maybe you can just go to the next slide.
We can get you a few more minutes, so that's fine.
Oh, okay. Well, anyway. So yeah, so the supporting requirements are intended to be sort of the list of the details that are required, and they're categorized into these few categories here: the knowledge, awareness, monitoring, adaptability, and so this is all the checklist items that you might need for a rover. We only have a few examples here; it's not complete. So knowledge is really meant to be what the system needs to keep track of over time. Awareness is what you need to monitor. What you need to be aware of in the environment. Monitoring is sort of what you need to have persistently keeping an eye on in real time. Adaptability is what you should respond to sort of surprises, let's say, and robustness. So these are sort of overlapping terms to some degree, but they give you a checklist that domain experts can sort of fill in for a specific type of system. So let's move to the next model. The next slide. Okay. So this is the goal model, where we take one sort of high-level goal or high-level requirement, such as the transfer, and we start breaking it down into supporting sub-goals. And here we have sort of two types of sub-goals. There's the OR relationship, where you can say a parent goal can be achieved by one or another sub-goal. And then you have the AND relationship, where you say, in order to achieve a parent goal, you need two sub-goals, or two or more sub-goals. And once you get to the leaves, then you have requirements that are goals that are specific enough to be assigned to an agent. And at the very bottom, we assign each of these to an agent within our system. And this is really intended to be where we discover the actions, and we discover the agents within our system. So we move to the next slide. So this is the the agent interaction model, where we take all the agents that we discovered from our goal model, and we start to think about how they interact. The sort of the squares and the parallelograms are the events and actions that the agents are responsible for, and then we have sort of the messages that pass between the agents as they each perform their task. So we had the transfer agent before, or the transfer. So the goal model before was focused on the transfer agent, and you can see him down there in the lower left corner. And from the responsibilities there, we see a few events and actions that are particular interest to that agent, and we can see when those actions interact with other agents in the system. So let's just move to the next one. Yeah. I'll be happy to answer questions, but it's a little difficult to go through every note in every diagram in this time frame. So this is the agent decision model, which vaguely resembles a state machine, where each sort of rectangle is an action or sort of behavior that the system has, and at certain events the system changes behavior. When the system changes behavior, you're expected to respond differently to incoming information. So it really shows, in response to a certain event, in response to a certain percept, what really should the system do. So the ideal situation, the ideal goal here is to be able to identify if there are certain inconsistencies, that the system performs the wrong thing at the wrong time, or is in conflict with other goals. Because there are multiple agents within the system, and they each have their own goal to fulfill, and you want to make sure that they're not conflicting in such a way that they fail to achieve the overall goal of the system. Okay, so if you can go up to the next slide. I'll quickly go through some sort of key takeaways, things to look for in these models, criteria. For the goal model, in terms of completeness, have all the goals been enumerated? You can check if there are conflicting goals that cannot be achieved at the same time, essentially. Does every goal have a supporting sub-goal? And does it all terminate at a reasonable leaf node, a reasonable requirement? Has every leaf node been assigned to an agent? And we go next slide. So both so the agent interaction model is all about the information, like focuses on the agents and the information. So you want to make sure that you've identified all the information that is shared between agents. Such as what are the messages that need to be passed between agents? Are there any percepts that are used by multiple agents? And then are those percepts actually meant to be the same thing? Are they interpreted the same way? I've heard many anecdotes of a specification that says this data is available and two components use that data, but they interpret it in different ways. So even though it technically sounds like the same thing, they just because of misinterpretation, the system fails to do the right thing. So knowing where you have two components that are relying on the same thing, you want to make sure that they are, in fact, using it in the right way. You go to the next slide. So consistency for the models. If the So this is where we're talking about the idea that the agents are all essentially running concurrently. So you want to make sure that are there situations where the agent can be performing actions concurrently that they should not be in? Are there proper guards in place such that, well, I know for the Mars rover, the NASA Curiosity rover, one requirement says the rover should never drive while its arm is extended out. So you may have two separate agents. One is, thinking about the drivetrain of the rover. Another one is thinking about the arm. You want to make sure that there is, in fact, no situation where the two agents are, working on conflicting goals, such that one is moving the arm and the other is driving. And by looking at those, the agent decision models, you can sort of think, you can come to a conclusion about if that situation can arise. Next slide. So the different types of information can lead to different types of issues. So the percepts are really meant to be, live information streaming from sensors. So then you may have to think about what type of sensor error you may be dealing with. What do you do about false positives, false negatives? What type of noise could be interfering with it? And you can really track now, since you have a complete complete traceability, essentially what information is driven by the percept. You can try to understand if a false percept comes in, what could that trigger? Now, messages, you want to trace where does a message really come from. So a message can come from another agent, meaning another software agent, or it can come from ground control, a human in the loop, another computational entity. So being able to trace what is the real weight of one of these event-driven messages, and what if a false percept in one sensor leads to a message, can lead to the wrong behavior in a different component. The idea there being you can trace the cascading effects of information going through the system. Okay. Next slide. Okay, so in conclusion, we proposed a modeling approach to go from the early conception of an autonomous system and apply the modeling to a case study, which is meant to be sort of a surrogate for a NASA domain system. This is still sort of early work, but we intend to continue this, expand this in another SARP project that we have in NASA.
Is that it?
So, yep, that's it.
Okay. Sorry. So I'm going to see if there's any questions here in the room for you. Okay, we got one over here in the back.
Yes.
Hi, how does this relate to 40 RCS from NIST?
I must admit I'm not familiar with that. I'm looking to my collaborators here. So could you repeat that? What is that? 40?
RCS, it's a reference architecture for autonomous vehicles that was developed by NIST and the DoD. It's been used a lot in Army and military UAVs. It was also part of the DARPA Grand Challenge about one was 11 years ago and one was 15. So it was all about agents and starting at the sensors up to doing more things that required, the 4D was time. So some of the things had to be low levels of time, like interaction with sensors. As you went farther and farther up, you got into seconds, like route planning, avoidance is lower time than route planning, because you want to plan a long route but not run into a tree or a hole in the ground on the way while you're doing the route. And then closer, low time, that was the 4D RCS, but it was all agents interacting, and there's a reference architecture out there for that that's been pretty well developed.
Okay. Yeah, I feel like I'm familiar with that the architecture at a high level. I'm not sure that I remember it by that name, but I will definitely go check to see what the relationship there.
Well, I mean, I was trying to refresh my name because I couldn't remember who wrote the book and was the architecture lead, but Wikipedia will help you out on that one.
Yeah. So, but like I mentioned, there is a great deal of literature out there on implementing autonomous agents, and the goal really was to bring it to the requirements level, so you can start to apply certain abstractions to the requirements, and how you can do sort of analysis early on. So rather than it being an implementation approach, it's a modeling approach, and yeah, I mean we're certainly trying to sort of use the language from agent literature. But in terms of, I mean, you mentioned timescales. We're not explicitly, talking about timescales, but we do try to address the idea that things take time, and actions are not instantaneous, and the state space is not, conveniently controlled by your system in all cases. So you could certainly think about agents that are operating at different timescales, and the percepts we talk about are really meant to be sort of the low level, high frequency sensor data, while the sort of messages and events are sort of the bigger, longer timescale things. Something that happens once in a blue moon.
Okay.
But yeah,
Thank you,
but thank you for the comment, because I'm going to go back and look.
Okay, great. Thank you, Gajan. I think we're going to move on, since we're running a little bit behind, but I did want to give you